where we left off. Because I was trying to explain to you why on the one hand you have these kind of general epistemological arguments of Einstein that there's something wrong with the idea of an inertial frame. And of the whole idea that there's a distinction between inertial frames and non-inertial frames, which makes the principle of relativity a restricted one, and why there's something philosophically better about sort of getting rid of that restriction and having a general theory of relativity. So one of the things I was trying to impress on you last time was that that's in one sense, a very old argument, because you find it in Leibniz. Well, why doesn't Newton recognize all motions as being equivalent and not just rectilinear motion? But the answer back then was perfectly obvious, because we have this principle, that it's the principle of inertia. And that's supposed to be a fundamental law, that there's something special about the straight lines of space-time, is how we would put it, or how they would put it, how Newton would put it. There's something special about a uniform motion. And that's what all of our physics is based on, right? The whole idea of force that they had back then only makes sense against the assumption of the natural state of motion the bodies would be in if a force weren't acting on them. But, so people like Leibniz couldn't really get rid of that idea. So there were two aspects of Mach's critique of that, of that idea that stand out versus everything that ever happened before, where there were just people saying there's something wrong with it, but incapable of making a coherent argument for getting rid of it. And so Mach had these two arguments. One is that we don't really have to get rid of the law. We should just express it in a way that respects how little we really know, right, about the circumstances we live in. In other words, when we state the law of inertia, we shouldn't state it as if it applies just to space and time. Abstractly, we should state with respect to whatever it is we're actually measuring it with respect to, and that is the fixed stars. Because we don't know, if you took the stars away, whether it would still be true that a body moved uniformly in a straight line. Right? All we know is, the evidence we have is that every time we look at a motion relative to the fixed stars, we can identify the force that's causing it. Whereas if you look at a motion relative to the Earth, you can't find the force that's causing it, because it has these centrifugal forces which have no cause, right? I mean, there's no force pulling something away from the Earth. Right? And the other of the 2 points Mach was trying to make was that you could imagine different laws of physics in which it really did matter whether the stars were there. That somehow, this is one way that in 20th century people made this into a slogan. Well, masses over there determine inertia here. There was this principle that became known as Mach's principle, which is to usually identify with the view that somehow the very existence of inertia, and the fact that bodies have a tendency to continue in a certain state, is imposed by the distribution of masses in the universe. So that was Einstein's answer to this, what he thought was a puzzle. Namely, if you have two bodies relatively rotating, one of them is bulging out at the equator, what is the cause of the difference? And Newton says, well, the cause of the difference is this one's really rotating, because you can always tell, because having centrifugal forces is the criterion of really rotating. So if space were empty, and you started one of these moving, rotating, then that one would experience centrifugal forces. But Einstein says, well, now you're blaming this on space. What you should be doing is tracing an observable effect to an observable cause. The observable cause being the distribution of mass around the universe. Right? That's in a sense what Mach's principle says. The inertia locally depends on the distribution of mass globally. So what I finished up was explaining why the peculiar nature of gravity somehow takes this abstract idea of Einstein's that we shouldn't be tracing observable causes to observable effects to unobservable causes. It turns into a real physical argument when it's connected with the whole problem of gravity. Because if you remember Newton's theory of absolute motion, what was the real theory? What did he really mean? This is what he was trying to say. You have the sun, you have the earth, and you have all the other planets, right, scattered around. If you want to know what's in the center of that system, right, is it Earth-centered or Sun-centered? You basically have to find an inertial frame. Find the center of mass of this system, then you'll know, whether the sun stays more or less at rest or the earth. Because once you find the masses in the system and the forces that are at work, then you can say for sure, well, the sun is the largest mass in the system. The center of gravity will always be close to the sun, and therefore it physically makes no sense for this whole system to be revolving around the earth. It's physically impossible. So he goes, according to Newton, you go from this kind of argument that Copernicus himself made. Well, look what a much more plausible hypothesis it is for the sun to be revolving around the earth. For the sun to be in the center. It's much more plausible. But then Newton says it's not a question of plausible arguments. It's a physical system. And all the parts of it interact. And the only part that can stop interacting, the only part that isn't going to move, is its own center of gravity. It's not a body, it's a point in the system. Right? Because every body attracts every other body. The sun can't just sit there at rest. The earth can't just sit there at rest. They both kind of wobble around depending on how they are being pulled by the other gravitational sources. So Newton's idea was, well, the only part that stays at rest is the center of gravity. So if you find the center of mass frame of the whole solar system, you find, well, the sun is always very close to that. But then Newton had this relativity principle that said, if you said to Newton, well, how do you know that the center of gravity is at rest? He would say, I don't care, because it's going to be a sort of Copernican heliocentric system, more or less, whether the center of gravity is at rest or moving uniformly in a straight line. And therefore, the Copernican system, in this ironic Newtonian sense, is kind of almost true, given that Copernicus was basically wrong. The sun is not in the middle of the universe. It's not at rest. But the system is sun-centered in the sense that the sun stays very close to the center of gravity while it wobbles around, and all the other planets revolve around it. And that center of gravity frame is an inertial frame. But then even Newton himself noticed this other fact that's almost like a relativity principle, which is that if you imagine that there was some other system, like some other huge mass far away, and that all the parts of the solar system were accelerating toward it, it would still behave exactly the way it does, because that system is too far away. Or if it wasn't too far away, then you'd notice, right? You'd notice that there's always some acceleration of the parts of the solar system converging on that source. Since they don't converge, the source must be very far away, if there is one. Of course there is, right? The center of the galaxy is holding the solar system in a slow orbit. I mean slow in the sense of how long it takes to complete it, not slow in the sense that it's moving. And it is fast. But, so what Einstein is essentially telling you is that he's sort of reviving these Newtonian arguments and saying, actually, if you can't tell whether a whole system of bodies is in an inertial frame or being accelerated, then maybe there is something wrong with the idea of an inertial frame after all. Now, how you get from there, I recapped everything from last week just now in the past 5 minutes, just as the next step is, you know, a lot more complicated, I would say. How do you get from saying gravity is a mysterious force that makes you question the idea of an inertial frame? Because you can't tell empirically whether you're in an inertial frame or in a falling frame. I remember that drawing I made last time. You have a box, you and everything in the box just sort of falls to the earth from a great height. Well, when you're inside the box, you'll feel as if there are no forces acting at all. People who are in a weightless state in orbit feel as if no forces are acting at all, even though gravity is acting. Right, you can, you know, if you are in this box and it's thrown off a 120-story building, basically until you get to the bottom, you'll be thinking, you won't know that you're not in an inertial frame. Everything will just be sort of floating around. Like in that famous old joke of the 20th century. What did the man who was thrown off the Empire State Building say as he passed the 40th floor? So far, so good? There was a cartoon that I used to see on TV when I was a kid called The Pink Panther. And somewhere during the credits, there was, I forget what was going on, but he was in a house that was, you know, thrown up in the air and fell down, or fell in a box that fell off an airplane. But it's like a house, because he's standing at the door and it's falling. And it's about to crash to the earth, but you know, just before it hits the earth, he just lightly steps off. And he's fine, and the house gets crushed, of course, as it falls from a great height onto the earth. Now, see, if you never saw that, so you have a better chance of understanding gravity than generations of children who were brought up with this utterly confused view of the situation. Countless children from my age cohort were killed thinking they could just jump out of falling structures at the last moment and be totally safe. It's true, right? Got stats on it. But those arguments I explained last time about you know, someone floating around in a box, those are really powerful arguments because they tell you, on the one hand, gravity is really peculiar. And on the other hand, because gravity is so peculiar, it acts the same way on everything, right? You can't imitate it with some other force, remember I was saying last time, or last week. Right? You can't really imitate gravity with some other kind of field. Because the trick about gravity is how it acts exactly the same way on everything. But because it acts exactly the same way on everything, it's hard to distinguish from inertia. If you're falling in a gravitational field, it's hard to detect evidence that you're not just moving uniformly in a straight line. Now, of course, there's something, if you were Newton heard this argument at the time he lived. Well, in a sense, he did, right? Because he made it himself when he said, look at the system of Jupiter and its moons. You can treat it as if it's at rest or moving uniformly in a straight line, even though it's in this powerful gravitational field being pulled into the sun. Or, look, the whole solar system, you can ignore any external field acting on it, because if there is an external field, it's acting almost equally on everything, like gravity. Because of course Newton would have thought, and it is rightly so, that the most plausible case of the whole solar system interacting with something else would just be some other masses out there and their gravitational pull, right? Like the gravity holding the galaxy together. Of course, he didn't know about galaxies. Nobody knew about galaxies back then. But if there's maybe there's some other weird force out there that can act in long range. But, the most plausible candidate would be gravity. The gravity at the center of the galaxy would hold it all together. But still, in our solar system, we can pretend it's an inertial frame. So if you ask Newton, well, what about this idea of an inertial frame? What about the idea of the true acceleration of a system of bodies? Because Einstein's argument is basically saying, you'll never know, right? Because you could say, if I'm standing here, right, and I let go an object on the Earth's surface, I'm in this box, I let go an object. Its acceleration is 9.8 meters per second downward. What's my acceleration? Nothing. Right? I'm just standing here in a static field and I'm feeling my weight on the floor. But then Einstein says, well, but if the box is moving upward at 9.8 meters per second in the opposite direction, then you don't have it doesn't have a downward acceleration at all. This ball that you let go of isn't going anywhere, right? It's just behaving inertially, and the box is moving up, right? And you're not feeling your weight on the floor, you're just feeling your own mass, your inertial mass, which is resisting the upward acceleration of the floor. And because gravity affects everything equally, you won't be able to distinguish these things. Whereas nobody ever should mistake a magnetic field pulling down with gravity, with an inertial resistance to going up. Because not everything is affected by magnetism, right? Magnetism isn't like inertial resistance. Because only some things are affected by it. So what's the acceleration of this ball that you let go of? Is it 9.8 meters per second downward, or is it nothing? Is it just resisting being accelerated upwards? Right? If you're holding it in your hand, you're feeling its downward acceleration. You're exerting a muscular effort to prevent it from following that, right? But if the floor is pushing your feet up and your feet are pushing the rest of your body up, then basically that ball isn't accelerating downward, it's resisting being accelerated upward. So what is the true acceleration? Similarly, if the box is, if the box is dropped off of a tall building, right, and then instead of feeling your weight on the floor, you're just sort of floating in it, right? What's your acceleration? Is it 9.8 meters per second? Well, you don't get to measure that, right? It's zero as far as you're concerned because you don't feel it. And so this is a very Newtonian thing to say, because Newton would say, if you're an inhabitant of Jupiter, well, what's the acceleration of Jupiter? Well, maybe it isn't anything. Maybe Jupiter is covered with cloudy gases and you never see the stars or anything like that. But you have delicate instruments to measure its acceleration. You say, well, this whole system is not accelerating at all. right? Because it behaves as if it's not accelerating, right? Is the acceleration something, or is it zero? And so Newton's answer to this was, well, you know, it can't really, if it's falling, it won't really feel exactly like zero. It just will be, the difference will be too small for you to detect most of the time. Right? If people are floating on the space shuttle, right, and they're just sort of, you know, their objects that they brought with them are just sort of floating around, you know, the things they brought with them are sort of floating, right? Why is that the case? Well, because Newton's laws tell you if the same acceleration is working on all parts of the system, then it's as if there was no acceleration working on it at all. I mean, that's really amazing drawing. But of course, that's not really the case, right? What's really happening is everything's falling toward the center of the Earth, right? If the space shuttle were this big, right, then the difference between something falling toward the Earth over here and falling to the Earth over here would be noticeable, because they're all falling toward the center of the Earth, and they should be accelerating toward one another. It's just that in a small frame of reference, it seems like an inertial frame because the differences are too tiny to detect. Of course, the moons of Jupiter are all, and Jupiter itself, are all being pulled toward the center of the sun, not in parallel lines, but in converging lines. And that's a real difference according to Newton. So he would say, well, you know, when the frame of reference is small compared to the distance of the source, then it seems like it's an inertial frame even though it's falling. So Newton would say, there's nothing wrong with the idea of absolute acceleration. It's just that it's hard to detect when the gravitational field is so homogeneous, right? It seems homogeneous because the source is so far away compared to the size of the frame of reference you're looking at. Okay, so the real acceleration, according to Newton, of the Earth, right? Well, it's acceleration relative to the center of mass of the sun, right? Plus whatever acceleration the center of mass frame has in virtue of being pulled toward the center of the galaxy, plus whatever acceleration the galaxy itself has, and so on. It's just that, you know, it might be too small to detect these little differences. So Newton would say, well, you know, you might feel, if you're in the Jupiter system, that it's a system that is basically at rest in an inertial frame. But if you could sort of move away the clouds and see that it's orbiting the sun, then you would say, ah, now I understand. It really is accelerating. It's just that it's hard to tell within the system because the actions of the sun on all parts of the system are so nearly equal. But when did you be sure that you had the true acceleration? Well, in Newton's case, he would say, Newtonian gravity means there's a kind of infinite case in which you could be sure. Right? You figure out the acceleration of the Earth relative to the center of mass of the solar system. Okay, but then there might be an acceleration of that frame relative to a larger frame. Okay, then you take care of that. And there might be an acceleration of that larger frame. So if you really sort of push Newton up against the wall, he'd have to admit, well, it's true that I wouldn't be able to tell you the true acceleration of anything unless I could tell you where all the matter of the universe is. Because as long as I've got only a partial picture, then it might be that my inertial frame is actually falling in some larger gravitational field. And he actually thought about this, but his answer was, hey, luckily we don't have to care. Because the accelerations of all the bodies in the solar system can be figured out, and we know exactly how the system is structured now. It's basically sun-centered. The center of gravity is here, the sun kind of bobs around the center of gravity, and all the planets, including the Earth, revolve around it. And that's settled, and it doesn't matter if we're all falling toward some other distant thing. And so I've accomplished my task, even though I can't tell you the answer to that infinite question. But there's two ways of it being infinite, right? One is you could say, well, at the end of the day, meaning infinitely far from now, we might include all of the mass of the whole universe in one center of mass array. We'll find the center of mass of everything there is. Then we'd be sure. Now, how can we be so sure? Well, because according to Newton, you never have an acceleration that isn't caused by a force. That's why centrifugal forces aren't really real forces, although it's a real thing, but it's misleadingly named. Right? And so a real force has a real action and reaction. So the Earth can't the whole solar system can't just accelerate unless something's causing it to. Because nothing ever accelerates except when it's part of an interacting pair. So if you knew where everything in the universe was, you could be sure, well, there's nothing else left that could be causing the center of mass of everything to accelerate. But that's an infinite problem to solve, right? It would take infinitely long, infinitely good observation. Or you could imagine having infinitely precise observation, right? So that you could look at, say, Jupiter and its moons, right? So precisely that you could actually measure the tiniest non-zero convergence, right? You could say, well, the way given astronomical observation as it is, we can't be very precise about this. But if you could be infinitely precise, then you could say, well, if these really were exactly parallel, right? If the accelerations on all the planets were exactly parallel, if there wasn't any kind of convergence of these things, then there couldn't be something outside causing it. Because a finite body, no matter how big it is, if it has a gravitational field, the gravitational field will converge on its center. So if you could be sure, if you measure so precisely, there's not you could be infinitely precise and say there's no convergence at all of these planets in Jupiter's system, like the satellites in Jupiter's system. Then you could be absolutely sure there isn't any source pulling it towards its center. Because if you could be infinitely precise, you could tell if there's any kind of convergence toward the center. So if you said to Newton, well, isn't it true that because gravity is so peculiar, you never really know whether your acceleration is zero or not? You never know whether the frame you're in is truly inertial or not. And his answer, the only answer he could give would be, well, thanks to the third law of motion, I know that accelerations don't happen for no reason. So yes, I can be certain, as long as you give me an infinite amount of time and infinitely precise measurements. But short of that, well, this is good enough. Now, so this is why Newton he looked at all these phenomena. there are implications of A, his laws of motion, and B, the way gravity works. Because gravity has this Galilean feature of having exactly the same effect on everything at the same distance. So this is why Newton would say the sixth corollary to the laws of motion that says, bodies will behave the same whether they're at rest. A system of bodies will be the same whether it's at rest or in uniform motion, or if it's all being pulled by the same force in parallel direction. He would say, that's not really a new relativity principle. That's not an extension of the relativity principle. The relativity principle is the one that just says, well, there's no matter how precisely you measure, nothing would ever tell you whether you're uniformly moving or at rest. So this next principle, the sixth corollary, that's not a new relativity principle. That's just practically a relativity principle because it tells you if the world happens to have a weird force in it like gravity, then there'll be all these falling frames of reference that will look like inertial frames if you don't look infinitely precisely. So Newton would say that's the restricted relativity principle is the only real relativity principle. The sixth corollary, this seeming relativity of gravitational acceleration, is just a weird feature of gravity and a kind of practical indistinguishability, but not a true relativity principle, because in principle you could tell. It just would take infinitely precise observations over an infinite amount of time. Now, Einstein had several problems with taking this view. One is that he wasn't interested in the sort of infinite perspective. So you could say, well, in a way, general relativity could have happened first, before special relativity. Because Einstein could have looked at these facts about Newtonian gravity and just said, look, the distinction between inertial frames and accelerating frames is not an absolute distinction. Because you can't distinguish gravitational free fall from uniform motion in a straight line. And he could have built the new theory on that. Without figuring out, what to do about the speed of light looking the same in every frame of reference, or anything having to do with electromagnetism. From Newton's point of view, well, the relation between gravity and light wasn't clear. If light is a very small massive particle, then maybe it is affected by gravity, but maybe it isn't. If it's not affected by gravity, then in a way you could always tell if you were in an inertial frame. Because if you had, say, lasers bouncing back and forth between mirrors, but the frame was, your laboratory was falling in the Earth's gravitational field, and all the massive particles behaved as if they were, just floating around inertially, as if they were weightless. But if light wasn't affected by the gravitational field, you'd be able to tell. Right? Because this light bouncing back and forth between mirrors would it wouldn't keep going back and forth in the same line between the mirrors. It'd be it would look like it was bending away from you if you were falling. So in principle, Einstein could have taken these facts about gravity and said, let's build a new theory where the inertial frame doesn't play the same role. But in fact, he didn't, because the motivation came only after special relativity. And part of the motivation, of course, was just that they needed a new theory of gravity. I mean, this is kind of just a historical fact that you don't particularly have to remember, but once you have special relativity, right, and special relativity says a lot of things that have nothing to do with gravity at all. But one thing it does say is that nothing, it implies that it starts from the idea that the speed of light is invariant, and then it says, it derives the notion that no signal travels faster than light. So you can no longer have this Newtonian theory of gravity that says, gravitational influence is not affected by time. So the first thing people thought of who were interested in this question once they accepted once they accepted special relativity, right? When once you accept special relativity, you've kind of reworked the theory of electricity, magnetism, and light in accord with special relativity. Right? So there are various implications of that maybe we don't need to go into, but for example, the fact that the speed of light is the same in every frame of reference. But then electricity and magnetism are not the same in every frame of reference, because what looks like an electric field in one frame can be a magnetic field in another frame. But the main thing is electrodynamics is still a theory about waves that propagate through the field. So the first thing people thought of was, well, what about gravity? Well, we have to replace Newton's theory that gravity is this instantaneous action at a distance to make it compatible with the notion that nothing travels faster than light. We no longer have this Newtonian idea. At every moment of absolute time, there's a configuration of the universe at that moment, and there's all the gravitational forces acting at that moment. So that idea is gone. We need a new theory of gravity. We need to revise it somehow. And the most natural way to do that would be just to start treating gravity like a field, like the electromagnetic field, and say, well, now if I somehow disturb the mass of Jupiter, instead of instantaneously changing the configuration of the whole gravitational field, I have to think about it as an effect that propagates at the speed of light, or slower than the speed of light. According to general relativity, it propagates at the speed of light. So if you ever detected a gravitational wave, you could assume that the source that caused it could be calculated by how long it takes the speed of light to get here, because gravity waves, assuming they exist, propagate at the speed of light. In fact, there was I don't even know why they do this, but there was a kind of preliminary announcement, maybe we detected a gravitational disturbance just a couple of months ago. Anybody hear about that? Any update on that? I mean, I've kind of been out of it.
Just read it online. You've been following it.
Famous last word. When I read about it, just within the past 2 months, it was important scientists saying, oh, this is really exciting, we're not sure how excited to be yet, because we haven't really confirmed this. But everyone's excited because it might be something. But as far as I know, nobody's followed up yet. I mean, I'm sure they followed up, but nobody's announced a follow-up yet. But anyway, is everybody following anything? If anything I say puzzles you, you really should ask. So here's the thing. You might think, well, now that special relativity tells us the true structure of space-time instead of Newtonian space-time, well, then we just have to modestly revive Newton's theory of gravity to talk about it as a kind of, it's a little bit like electric charge, right? Or electromagnetic charge. You have these sources of the gravitational field, And you have disturbances that cause them to propagate through space in like a wave. And let's just make a theory like that. But the first problem you run into is just this problem, that with the electromagnetic field, you know what it means to say the absolute value of that field, right? When there's no electric charge or magnetic charge, you can actually say that it's zero. Okay, you can say, well, with quantum mechanics, that makes it a little bit fuzzy, but it's still fuzzy near zero, right? Whereas with the gravitational field, well, is it zero, or are we all falling incredibly fast toward the center of some distant galaxy? Well, there's no answer to that, right? You can't have a zero with the gravitational field. So you can't just rewrite Newton's theory of gravity to make it compatible with special relativity. So this is why the history went the way that it actually did. So Einstein has these two ideas in mind. One is, well, now that I've come up with special relativity, all of physics, presumably, has to be rewritten with this new space-time framework. So that's got to include gravity, but on the other hand, gravity won't fit into that framework in an easy way, because you can't just make it into a propagating field, because no one ever knows whether it's gravity, the gravitational potential is something or zero. For all these reasons, right? Is there a gravitational field holding me down, or is there no gravitational field at all? So Einstein decided, for all these reasons, that the problem of extending the principle of relativity and having a new theory of gravity were closely related. Because of this, I may have mentioned it last week, by introducing this idea of the observer in the box, right? His first thought apparently was, when he's sitting in his chair, thinking, well, if I and my chair were falling, I would not feel my weight on the chair. Which is the same thing as saying, if I'm falling in an inertial frame, sorry, if I'm falling in a gravitationally freely falling frame, then it feels just like an inertial frame. So it's this, he starts to think, well, there's something, he has this philosophical idea in his head that he already got from Mach. There's something wrong with this privileged character given to inertial frames. Then he gets a fact from gravity, which Mach apparently never considered. Nobody ever really considered it that carefully except for Newton. That an inertial frame and a falling frame can be indistinguishable. But unlike Newton, he considered it as a real possibility that this new principle really is a relativity principle. Right? That there's something wrong with Newton says, well, in principle, there's a distinction between moving inertially and falling in a gravitational field. Just that in practice, it'll always be difficult to work that out. Now Einstein said, well, let's make that into a principle. Like I said, as far as Newton knew, well, maybe light would be an exception to the rule that gravity has the same effect on everything. Einstein said, let's assume that it really does have exactly the same effect on everything, including light. There's no exceptions to this rule. Then maybe it really is a principle. Maybe in principle you can't distinguish inertial motion from freely falling motion. So in other words, he's taking this idea that Newton had, that in practice, the distinction between gravity and inertia can be ignored. Because you can treat a falling frame as if it's inertial. But in principle, that's a real distinction. Whereas, and that's the basis of this whole theory, right? What do we do when we analyze the gravitational motion of the planets? Well, you take any motion at all, because objects never move uniformly in a straight line. All right, well, here's the motion of the Earth around the sun. The basis of the theory is you have to be able to decompose this curve, right? And say, well, here's the part that consists of what it would do if suddenly all forces stopped acting on it at that moment. Well, it would move uniformly in a straight line, according to Newton's first law. Here's the part that's contributed by the sun. Here's the part that's contributed by the moon. Here are these tiny parts contributed differently at various times depending on how far Mars and Jupiter are away. And well, even Venus, right, has some small effect on the Earth. Well, they all have an effect on the Earth, right? Because the gravitational field goes on forever. But these are all the things that are not immeasurably small. And when you add all these things up, you get the actual motion of the Earth, and that's how it works, right? Because you start with this idea that there's the inertial path and all these components of acceleration contributed by the other bodies that are acting. Now Einstein says, well, that distinction is kind of a relative distinction, because if instead of saying the inertial path, you say, well, this path is actually, what we're calling its inertial path is inertial with respect to the center of gravity of the solar system, but that might be accelerating too. So it's not a good distinction anymore. Let's make this into an absolute principle that gravity and inertia are not fundamentally separable, but they are really aspects of the same thing. Because what looks like gravity in one frame can look like inertia in another. This is a really important point to get, because this is what the whole idea of curved spacetime is based on. I mean, so if you're struggling with this, you should ask for clarification, because this is, I mean, we usually give an example like this. It says, well, here's the path of a light ray, which looks like it's going in a straight line like this, but actually we're seeing a star that's behind the sun, so it's going like this, right? And the fact that light's traveling in this curved path means that space is curved. Well, in some vague sense that's true, but that's not where the theory comes from. That wouldn't justify the theory. That would just tell you, well, obviously light is affected by the sun somehow. But of course, Einstein already had the theory when he came up with this idea. He said, well, here's a test of the theory, if I'm right. It wasn't the basis on which he knew he was right. He knew he was right because of this, because he thought this identity of gravity and inertia was really a fundamental fact that Newton's theory doesn't embrace. Newton's theory tells you all the relevant facts about gravity, but it hangs on to this absolute distinction between inertial motion and gravitational motion. And I'm going to build a new theory on abandoning that distinction and a theory based on the identity of the two, and that's where the idea of curved space-time really comes from. I'll just let you go, but if you have, think about it. If you have questions about it, bring them next time. I'm embarrassed to have to ask this because I haven't checked in a few days. Has anyone posted anything on the forum? Did you post the thing?
Yeah, the video, yes.
Oh, good. Thanks. It was just at the last lecture?
Yeah, last lecture until YouTube.
Okay, good. Thanks.
Oh, no worries.
And are you taping this now? I didn't notice. I would have given it better. Well, no, I probably wouldn't have. I just wouldn't have.